So in this problem, we're still going to try to find the shear force and bending moment at a particular point, in this case point C. What's a little different from what we had before is we've got a distributed load. We didn't have a distributed load before. So again, what I like to do is just kind of sketch a cross section. I'm going to cut it there. And really I'm deciding whether I want to work the left side or the right side, and see if there's any advantage to one side or the other. We talk about the left side first. I'll need to find my reactions at A. And how many reactions at a pin? 2. So, and then on this side also I have a uniform load. Well, that's not so bad. On the right side, what's the difference? Well, I still have a uniform load, so that's the same. And I have a roller. So technically I have one less thing to find. You will be successful no matter which one you choose. But I always like to try to choose the path of least resistance. So in this case, I'm going to say I'm going to choose the right side. And once I make that choice, then I know, hey, I just need my reactions over here at B. So I'm going to assume that B acts up, and I'll call that BY. Now, just to be complete, I'll go ahead and make similar assumptions for my 2 pin forces at A, but really I'm not interested in finding those right now, so I'm not going to be too concerned. So looking at this whole structure as a free body diagram, how can I write an equation to find BY easily? Yeah, that's sum moments at A. So when I sum moments at A, I need to have the effect of this distributed load. Now, the easiest way to do that when you're finding for reactions is to come up with a equivalent load. So I have this distributed load, and I want to get an equivalent point load. And the way you find the magnitude of the load is to take the area under the curve. And that's easy. It's a rectangle. It's just base times height. So the base looks like it's 18 and the height is 3. So I know my equivalent force will be, what's 18 times 3? 54? Yeah. So that'd be 54 kips. And where is it located? Well, it always acts through the centroid of the area. That's easy for a rectangle too. That's right in the middle. So since I'm going to sum moments about A, I'll just go ahead and sketch in what that distance there is. It's half the distance. It's 18, so this will be 9 feet. So all I have to do then is come over here and sum moments about point A. I'm going to assume right-hand rule, and of course we'll set everything in equilibrium. So summing moments about A, I have the concentrated equivalent force of my distributed load. Has a force of 54 and a moment arm of 9. Is that going to create positive or negative moment? Negative. Negative. So I'll have minus for the moment, and then the force is 54 kips, and the length is 9 feet. So there's the moment of the force about A. Now what about the reaction? So you're going to create positive or negative moment about A? Positive. So we have positive moment with a force of BY and a moment arm of 18. So if you solve for BY, I think you get 27. That shouldn't be too surprising. It's a simple supported beam, uniform load. Basically, half the total load goes to one side, half to the other side. So it makes sense. Now with that information, I can come down here and now draw a free body diagram of the right-hand side that I mentioned before. I know BY, we just found it. I got a positive value, so I assume the right direction, so that's 27 kips. I have my distributed load. It has an intensity of 3 kips per foot. I know the length of this segment, 12 feet. So that's all I have on the right-hand side. Now I've made this cut here, so I have to look at my internal forces. So I'll draw a positive axial force at C. I'll draw a positive shear force at C. And I'll draw a positive bending moment at C. So those are all the positive sign conventions for my internal forces. Remember, shear is positive because if I look at this as my segment and the shear force pushes it up, the element would want to rotate clockwise. Right? This is positive bending moment because it would bend the element into concave up or a smile. And of course, axial load elongates the structure, tension. So now it's a pretty simple problem. Once you have the three-body diagram drawn, you just solve for your 3 unknowns with the 3 equations of equilibrium. Again, to make it easier for us, I'm going to, instead of dealing with the distributed load, I'm going to deal with its concentrated equivalent. So the area under this part of the curve that I'm looking here, this right part, is a rectangle, it's base times height. So that's 12 times 3, so this will be 36. And the distance, say from the cut edge to this centroid line is half the distance, or 6 feet. So now I have everything I need. So if I give you this problem on the exam, if you develop something like this, you're 2/3 of the way there, as far as I'm concerned. Because now you just apply your equations of equilibrium. It's usually a good strategy to go ahead and sum moments first at the cut. So we'll do that. And the reason I do that is that the shear force and the axial force are really concurrent at the point of the cut that I'm taking the moment, so they create no moment. So I get one equation and one unknown, the internal moment, and then balanced with all the other forces. So starting with the internal moment on the left-hand side, is that positive or negative moment with my sign convention? Negative. What about the 36 force, positive or negative? Negative. So negative moment, the force is 36, the moment arm is 6, and then the reaction force, it's the opposite direction, so it's going to be positive. And that'll be a force of 27 kips and a moment arm of 12 feet. So if you solve for the moment at C, I think it's going to come out positive. I don't know what that number is. Somebody's going to have to calculate that for me. I can't do that in my head.
108 altogether.
108?
Yeah, positive 108.
Anybody else get that?
Yep.
Cool. So that'll be 108 kip feet for the moment. It came out positive, so that means we have positive bending moment at C. Does that make sense? Well, look back at the original beam. How do you think that would deflect? Would points along the beam go up or down? Probably down, right? So you
wait a minute. On that right side, I got 108, so it would be negative MC plus 108. So I think it may be minus for the final answer.
No, I moved the minus MC to the other side. So what's all that? That's a positive number.
Yeah. Okay. I was just
So the deflection is going to be something like this. And if you look at it, you'll see it looks like everywhere in the beam it's kind of smiling. It's concave up. So we expect positive moment everywhere. So that seems reasonable. All right, so let's finish the problem. Simply find the remaining forces. Well, the shear force is all in the y direction. The axial force is all in the x, so that shouldn't be too bad. So if I sum forces in the y direction, make sure I have equilibrium. I'll assume up is my positive sign convention. So the shear at C is up, so that's positive. The concentrated equivalent is down. The axial force 27 is up. So it looks like the shear at C is going to be 9. Look right? I think so. And then last, kind of almost trivial, but let's check it anyway. If I sum forces in the x direction, make sure it's equal to 0. I'll assume right is positive. All I have is a force to the left, which is negative, and that's the axial force at C, and as you can see, it's 0. So I now know that at C, this point right here that we cut it, we've got positive bending moment, positive shear force. Any questions about that? We'll work a couple more in a second. All right.